Thank you. Thank you. Before starting, I'd like to open with a short preface. For those of you who've seen my first presentation 2 years ago, I've read or have read my blog post last year about why an engineering company chose to migrate to D. This is essentially an update on the status of that project. But there is a deeper message too. Yesterday, one of the questions Leith asked was, who of you would like to use D at work but isn't? Yeah. My estimate was that about 1/3 of you raised your hands. And I think outside of this room, in the larger D community, it's possibly more. For all of you that fall into this category, I hope that my story can be a source of inspiration. I've been in the same situation for many, many years. My advice is, keep an open eye for any opportunity, however small. Be creative in that search and keep trying. When you see an opportunity, step into it and be prepared to take personal risk, real risk. If you're asking your employer to use or move to a different new programming language, you're asking him to take a considerable risk. Demonstrate that you have enough confidence to take comparable risk. Invest your own time. Real risk means there is a real chance of failure, so be daring. Are there bindings missing? Write the bindings. Is there a library missing? Write the library. Are there language deficiencies? Write the DIP. Is there a transcompiler missing? Write the transcompiler. Don't just wait and hope for the language to become more popular. Take any small opportunity and do your best to make it a bigger one. That's the message I'd like you to take with you from this hour. I'm very happy that I'm not the only one using that strategy, so that's great. Come join us, make it happen. Now, a transcompiler. What's a transcompiler? It's a translating compiler that takes as its input source code in one programming language and translates it to another programming language. We differentiate between the source language and the target language. And both perspectives have are different, and they're both mutually exclusive. So the first one, intermediate representation, it's like the target language is sort of like an intermediate representation, like the very early C++ compilers that compiled into C and let the C compiler take it over from there. Or a more modern example, the NIM language that compiles into other languages. And the other perspective is if you're porting a program system, software system from one programming language to another. And they have different requirements. So in the first case, the process needs to be very efficient. It needs to be flawless. And you don't really care what the result looks like. It's going to be fed to another compiler. And so you don't want user interaction. And it's a very repetitive, you're going to do it again and again. And what you want to use is the source language. You're not interested in the intermediate representation. In the other case, it's the other way around. You're looking for greener pastures. It's a permanent move, and you do it only once. In this case, you do care what the results look like. You're going to use it and to look at it from now on. It doesn't need to be a perfect process. You can allow yourself to be pragmatic and with user interaction, give an opportunity to make the conversion correct. In this case, you don't want to use the source language, you want to use the target language. This presentation takes the porting perspective exclusively. This is a story about moving to D. not only are we transcompiling into D, we are implementing the transcompilation in D as well to keep things interesting. Now, I am a ship designer, not a chip designer, but a ship designer. I learned how to design ships. I earn a living by developing software for the design of ships. So why would I be talking about transcompilation? In short, SARC, the company that I work for, has decided to port all of its software that is currently written in extended Pascal to D. This is quite an endeavor. Last time we counted, we were at 500,000 lines of code, and we are using D to mechanize most of this process. Our software is used at shipyards and design offices, as well as on board of ships. We use the software ourselves, in-house, to do consultancy work, and most of it is still actively being developed and improved upon. So it is important to us that the porting process does not interrupt this business. As far as I'm aware, this is the second big transcompilation project to D. The first one was the conversion of the DMD compiler frontend from C++ to D, done by Daniel Murphy. He presented at DConf 2015. I met him at DConf 2017, and chatting with him was encouraging. Our approaches are similarly pragmatic, and one commonality between the two projects is that both span several years. So if this sample is representative and you're in for a transcompilation project, be sure to pack lunch. So I was going to make a nice animated timeline here, but you'll have to do with this free stock image. It's not relevant. The YouTube stream can't focus on me. To give you an impression, no. Here, the story. This is our story. So SARC always used Pascal since its inception in the early 80s. And the language has been working well for SARC. For a long time, there was no question about moving to another language. When I started working for SARC in 2016, I got to write a new front end to their computer-aided design software in C++. Still, the kernel of that software and all other parts of the software suite remained in extended Pascal. The thought that any of it would be rewritten in another language was silly at the time. Would have been silly. But around 5 or 6 years ago, sentiment started changing. Our extended Pascal compiler vendor had disappeared from the internet, and people started talking openly that if SARC were to still be in business 20 years from now, it should probably start looking for alternatives. D was not an obvious savior, but it got me thinking how I could demonstrate its power and simultaneously make D an attractive alternative. I thought, if D is as powerful as I think it is, I should be able to write a parser for extended Pascal in D. That would make an interesting and compelling showcase, and it might help translate extended Pascal code into D. It was in 2015 that I started work on that project that I pretentiously called Pascal 2D in my own time. Pascal 2D uses an amazing parser generator written in D called pegged. Pegged follows a language formalism popularized in 2004, quite recently, called parsing expression grammars, or PEG. It basically takes a string that defines a peg in a convenient format not unlike BNF, Buck's-Now form, and generates code that implements a parser for the language described by the peg. Working on Pascal 2D was fun, and I was gaining confidence in D. I basically just needed to type over the ISO specification of extended Pascal, and as I progressed, it succeeded parsing more and more of the language. Until one day, the parser kept running out of stack space, somehow getting trapped into an infinite recursion. It was only then that I learned about a common limitation of most PEG parsers at the time, namely that they do not support left recursive grammars at all. And extended Pascal appears to have several nasty hidden and intersecting cycles of left recursion. At first, I thought that this was the end of my endeavor. It was quite a depressing time, but I don't easily give up. It took the better part of 2016 studying the problem and researching recent publications. And thankfully, after several iterations, I finally managed to extend PEGD so that it generates parsers that support all kinds of left recursion flawlessly and without users even needing to be aware of the phenomenon. That was my biggest feat in DLand so far. Then came DConf 2017, and you can watch my presentation back called Extending PEGD to Parse Another Programming Language 2 years ago, to learn more about the business of SARC with movies, how PEGD works, what left recursion is, and how left recursion is handled. You can use that knowledge also for other parser generators. The status at this point was that I could parse 10,000 lines of extended Pascal files without the parser terminating prematurely, and the output being giant parse trees. Generation of decode was only possible up to Hello World as a proof of concept. This was enough for SARC management to decide that the time had come to actively evaluate various programming languages, and D would be one of them. It meant I could finally charge for working with D. The evaluation process took another year, and you can read about that process in the earlier mentioned blog post. In the end, to my excitement and horror, the choice fell on D. Now it is upon me to deliver on the promises and expectations that I helped create. And my estimate at the time, last year, was that it would take me another man-year to get a working translation of our software suite. And that was 11 months ago, and I have been spending roughly 50% of my hours on this project, and I think I'm still on track. And to give you an impression of how the transcompiler works, I'm going to share with you a very early version of it from nearly 4 years ago. It performs transcompilation of Hello World from extended Pascal to D. And it does it in 263 lines of code. The whole thing fits on a single slide, as you can clearly see. And that's including the unit test. Wow. As you see, maybe I can sketch a bit. As you see, it takes a string in extended Pascal. It feeds it to a function called EP or ep, whose output is fed into another function, 2D, and the assertion checks that its output is equal to another string, which is the D equivalent. Now, obviously, the magic happens in the EP and 2D functions, so let's look at those in sequence. The EP function is generated by the grammar function from PEGD. That is our only dependency. The grammar function takes a string as input that describes a peg for the extended Pascal programming language, which takes up half of our file. You only see the top bit of it here enlarged. From this string, the grammar function implements a parser for which the code is mixed right in. Line 6. We don't get to see it. It will be generated during compilation, but we can use it. How it is able to do that is outside the scope of this talk, but much of the workings already presented at DConf 2017. The process is not unlike the transcompiler you're looking at, except that the input and output are different. Let's look at a different section of the grammar. Line 221, for example, a compound statement consists of a begin literal, followed by a statement sequence, followed by end literal. Very clear and understandable, and very similar to the text of the standard document. In its turn, statement sequence is defined on the line above it and consists of one or more statements separated by semicolons and optional white space and comments, and so forth. And this sort of information is enough for PEGT to automatically implement the EP function. Now on to the 2D function. I have collapsed the two nested functions for the moment. As mentioned earlier, 2D takes the output of EP, which is a parse tree. A parse tree is a struct defined in PEGT consisting of the data members you see here. The most important ones being name is the name of the node in the tree, which is derived from the production rule in the grammar. So the statement sequence rule produces nodes with the name ep.statement sequence. The string input is a reference to the complete input, and members begin and end are indices into this input. So if you slice the input between these indices, you get the complete matched slice. Most importantly, the children member contains the parse tree child nodes, and this is how the tree is built up and can be traversed. Now, the imports container you see on line 162 is a set of modules that should be imported by the translated code. And this set will be filled during the translation. The code variable on line 236 is filled by the nested function translate_any, which does the actual tree traversal. When that's done, the set of imports is converted to an import declaration on line 240, which is prepended to the code and returned from the function at the bottom. The real work happens in translate_any. So what does it look like? In translate_any, we have a utility function, translate_children, that just traverses the direct children of a node and concatenates their translations. The engine of translate_any is a large switch on the name of the node, on line 180. On a side note, this looks like low-hanging fruit to make PEGT more performant, as having a giant switch on strings may not be the best idea from a performance standpoint. Given the popularity of PEGT, it is currently, yesterday, it moved from place 26 to 22, I believe, of most popular packages on Dub. Quite surprising for a parser and generator. So maybe someone ought to look into this and improve it. Anyway, on the last line, you see that many nodes are just recursed into with translate children. Like statement sequence, we are not interested in the fact that it is a sequence. We just translate all statements and concatenate their translations. A more interesting part of the switch is this. You see compound statement on the first line that consisted of a statement sequence surrounded by begin and end. The literals were dropped from the parse tree. And they will now be surrounded by curly braces. In Pascal, semicolons are statement separators, but in D, semicolons are statement terminators. So on line 215, you see that every D statement is followed by a semicolon. The next two cases, character string and apostrophe image, take care of string literal translation. On line 224, procedure name and string character are examples of slicing the input verbally, producing, for example, the identifier right line in the hello world example. The default there traps anything that the transcompiler does not support yet. So for the early versions. So that facilitates stepping up the compiler complexity bit by bit, involving trying more challenging input, adding missing bits in the grammar, and filling in the blanks in translate any. So that's all that's needed to pull this magic off. One small comprehensible file. I find this pretty amazing. But if you think this is cool, watch this. There's no main function yet. So let's add a main. We're at module scope, but instead of writing a D main, let's just do a mix-in. Write some foreign code, followed by app2d, and would it work? Of course it works. Hello D's world. We have effectively written main in a foreign language and with minimal annotation, and it just works. Apart from the 2D function, there's hardly any D code in this file. Think about it. I can't look at this code without a big grin on my face. Just imagine what goes on here, well within 300 lines of code. A peg is interpreted, which in itself is a domain-specific language. A parser is generated. The parser is executed to interpret foreign code in yet another language and converted into a parse tree that is then translated into code that is subsequently compiled. The power, not what it can do, but what I can do. If needed, I mean, we are not going to write code like this, writing Pascal and having it be translated on the fly. Once we have completed the port, we're going to write D code. And most of our code is just boring procedural code that could have been written in many other languages. But when we need to, we go all the way and use whatever tricks available to get what we need. Even currently, within this outdated language, we're using thread pools, free lists, shared memory between processes, SIMD, GPU shaders, even assembly. And this display of power shown here just screams, use me. D is going to serve the complete spectrum from beginning programmers to code magicians, all in the same language over a wide range of programming domains. However cool this is, this approach is not the most productive. The grammar doesn't change all as much, and regenerating the parser every time is like recompiling DMD for every invocation of it. We'll address that in a moment, but first this intermezzo. Now, calling Pascal 2D a transcompiler is overstating quite a bit, and I apologize to the compiler writers in this room. It's more a transparser. It doesn't do any of the hard things that compilers do after parsing, like semantic analysis, sensor by error reporting, and code generation. It doesn't maintain scope information or even keep a symbol table. It doesn't support modules. It does as little as possible and relies on similarities between the languages to preserve semantics, and that the program still does the same thing if you microtranslate its molecules literally. And ambiguities often don't matter. We don't care what types A and B are. In fact, they could be variables, but also function evaluations without arguments. Probably there are parts in the grammar that are never traversed because the ordered choice operator of peg goes with the first successful match, and that's often okay. It's like taking apart a building or a city, processing the bits, the bricks one by one, piecing them together again, and then expecting to get buildings back that have the same structural integrity and a city that's operating in the same way as before. It works in our case. Now let's fast forward to 2 years into the present and see how I've organized the transcompilation process without interrupting production and daily business. So first thing is to split this single module into 3 main components. First comes the grammar and generation of the parser. Second, the translation code. And third, the main function driving the process. Let's focus on the parser first, which obviously has grown considerably. The PEG string has been put in its own file as a string constant, currently counting some 800 lines. You see the top here. Previously, we used the grammar function from PEG to generate plain code ready to be mixed in. But it is much more efficient to write it to file as a separate module instead, a D module, so that the parser does not have to be regenerated if the grammar does not change. This is accomplished by the PEG function as module, for which I have written this very small program. So if you call rdmd generate D, which is the complete file here, it will dump a parser for the PEG defined in appgrammar into the file appparser.d. rdmd is just a very handy variant of dmd that compiles and runs a D file in one go, and if the source hasn't changed, it skips compilation and invokes a cached executable. The generated module will additionally import a module called actions, which contains some semantic actions, which is an advanced feature of PEG that allows manipulation of the parse tree while it is being assembled. But instead of calling rdmd manually to initiate generation of the parser, I wrote a small program to do that for me. Because that is only necessary if either the grammar or the generate D script changes, or indeed this script. So I use an underscore file here. We're actually just scripting with D at this point. The program takes one argument that you see being used on line 15, which is the location of the PEG library. More on that in a second. And instead of invoking rdmd on the make script manually, I've created the dub package for the transcompiler that does that for me. Dub is the standard package manager and build tool of D, and these are the sections of its configuration file relevant to the parser generation. We've excluded the files that it should not compile automatically, because that's part of my custom build. And we include an invocation of our make script for every build in the pre-generate command section. Note how the location of PEG is filled in automatically by dub with the PEG package dir variable. This will work whether dub is automatically fetching PEG from code.dlang.org, the central package repository, or whether I've configured dub to use the local fork of PEG when I'm working on PEG improvements. And that's how the parser is conditionally generated every time that needs to be done. That is a conversion of 800 lines of PEG to a 19,000 line parser implementation. You see the definition of the EPIF function on the very last line there. There have been discussions on the forums lately that dub is insufficient for more complex projects. But although there surely is potential to improve dub, I think this illustrates that as long as you can fall back to pure D, it's okay. It's okay for me. It's working. Except for a regression. There are currently problems if the generated file does not exist at all. This is especially annoying in continuous integration. I found workarounds, luckily, but if you want to do me a favor, please look into the regression and include examples in the test suite of dub. The second part was the 2D translation function, which now also lives in its own module and has grown to some 4,000 lines of code. You'll see the end of that file here. Lastly follows the main program that does some argument processing and calls the EP and 2D functions. Here I should note that Pascal modules consist of an interface part and an implementation part. And these parts can be defined in the same file or be split across two files, a header and an implementation header and pass file, mainly to facilitate circular module dependencies. In the latter case, both these file names are passed as command line arguments. And the main function will just concatenate the files before feeding them to the parser. So the three parts of the transcompiler that we have seen here are part of the same DUB project. In addition to the transcompiler, I'm writing a library called appcompat, which implements functions from the standard library of extended Pascal. Some of the functions have direct equivalents in Phobos, in which case the transcompiler just inserts the correct imports and calls. But in other cases, it is just easier to implement the functionality myself. appcompat is a DUB sub-package of Pascal 2D, such that translations can directly depend on it, and it always is in sync with the transcompiler. Lastly, there are some basic tests where the results of translations are compared with expected outcomes. These are run by RDMD script that also calls DUB test for the transcompiler and the library, so that unit tests are done. All these are stacked together in a Git repository, which itself is a Git submodule in a larger Git repository containing the complete translation setup for our software. Inside it, we check out a complete subversion working copy of our Pascal sources. And these are, of course, frequently changing by commits from my colleagues. And conversely, the changes that I make to the code to make it translatable get merged into production code. In addition to this working copy, this master Git repository contains several subdirectories for libraries and applications, each with a DUB configuration file describing dependencies between them. The actual transcompilation is driven by an RDMD script that selects individual Pascal modules from the subversion working copy and places their translations in the appropriate DUB project directories. Let's have a look, just for the fun of it, at what those instructions look like. First come the input files per module in an array, then some function called tr with an output file name. The last row on this example shows where both the module interface and implementation are defined in a single file, yielding one input file. The middle row shows an example where interface and implementation are in separate files, yielding two input files. And the top line shows an example where there is only an interface file through an externally defined library, which is translated into a DI interface file. Now these lines are written using uniform function call syntax, meaning that what comes in front of the dot is actually passed as the first argument to the tr function. So if you look at the tr function, we see that it takes an array of one or two strings, and its first argument as its first argument, and an output file name as its second argument. Now actual translation only needs to happen if the transcompiler changed or any of the input files changed. So we note down the target time as the time the target was last modified, or a very early time if the target doesn't exist yet. The time when the transcompiler was last modified is taken at program startup at the top of this section. So if the target was modified after the transcompiler and after all of the one or two input files, then we do nothing and return early. I find this very concise code and easy to understand. Otherwise, we spawn a new process in which the transcompiler is called with the input file names and direct output to the output file. We wait for this to complete and verify that the process succeeds without errors. Immediately after the translation, we run the deformat tool, which does an excellent job at formatting and indenting the translation, so I don't have to worry about the aesthetics of my output all that much. After all translatable modules have been translated, the only thing needed to build the entire thing is a call to DUB build on the application, which kicks off compilations and dependencies wherever necessary. The current state of this project is that some 40 plus modules are in the translatable set, which makes up an important part of our library files. It's still insufficient to compile in production applications, but sufficient to compile some smaller test programs to see if the translated libraries work as intended. You'll see some of that in a moment. The next days, I will work towards doing some number crunching involving loading of a hull shape and performing numerical integration to see if the computed results match between languages. So how did I get at this set of 40 files? I started by doing a make clean in the Pascal working copy and then looking at the order at which Pascal files are compiled thereafter. The first two files were leaf modules, and they went through with relative ease. It became interesting when modules started importing other modules, because I wouldn't make progress before also translating those other modules. The other modules also had imports, so this was quickly getting bigger and bigger, and I didn't know where it would stop. And apart from continuously fixing general deficiencies in the transcompiler and appcompet library, for every new file, I had to go through some typical stages. Case sensitivity. Pascal is a case-insensitive language, so there appear to be all kinds of mismatches all over the place. It, and some places uses identifiers that happen to be keywords in D. The type conversions that are implicit in Pascal but need a cast in D. Dealing with immutable strings, mutable strings. Calls into the Win API that need an ampersand an argument in D because the API is differently defined in D and Pascal. And for each of these cases, I would get a new compiler error, you know. And after fixing those, I would get another undeclared identifier error needing another import and repeating the same kinds of fixes there. You're making progress in some way, but the finish line seems to be moving at the same pace and you wonder when it will stop. After doing this some 40 more times, I finally reached a point where it didn't complain about undefined identifiers, but instead it gave a compile error in the files at the very top of the list. Turns out we entered a new compiler path with different kinds of errors that needed fixing. After completing that iteration, I hit on circular dependencies and module constructors. Finally, after the nth try, no more errors. Did it generate a library binary? Yes, it did. Sorry. So now what? The 40 lines are still too small a set to link any of our applications. So we wrote a small program using this library to see if it would run. Guess what? Icon resource missing. This actually made me cheer out in celebration, because this pop-up contains our text, and the pop-up it brought up is brought up by our GUI code, relaying a system error. So for me, this was like the first ping home from a Mars rover having landed successfully. The resource file was quickly added to dub, which made the pop-up disappear. In its place came a segfault that I don't remember the cause of. But from there on, it just has been a matter of identifying problems and fixing them. This is the current state at the moment, showing a very simple program. Let's see what it gives us. It starts up and asks us to select a project, so there's at least some file I/O going on. And icons in there, the menu is working. Can change the font size. Mouse input seems to be working, refreshing. User inputs. Extra rows added. Another text entry. Removing rows. What other things can be done? Spawning an external process. This fires up the company website. That looks good. Let's try and print something. That's a missing logo. Print preview seems to work. And I forgot to show you a printout, a real, tangible, which is the best printout I've held in my hands in years. Real proof. So what does it do there? It changed some colors and preferences, brings up another dialog, radio buttons, checking user input, and we'll have to stop the demo there before I run into funny issues. Okay. Now, since I've chosen to keep the transcompiler simple, without any of the other typical compiler passes, there will be times that it doesn't do the right thing. So here are a few tricks that I apply correcting those cases, some of which make use of unique D features. Let's see how many we can cover of them. This is a Pascal program on the left that translates to D on the right. Let's say that complicated stuff does not translate correctly. I can surround the complicated stuff with two specially crafted comments that are recognized by the parser. P2D substitute begin and P2D substitute end, and the parser will skip everything that comes in between. I can then write a manually coded cleverness inside first comment that will substitute the complicated stuff in the D translation. Well, instead of defining escape rules, I'm using these similar but seldom used characters. Oh yeah, this is about what happens if the cleverness should include curly braces. So I use these other symbols. Now let's say that I'm busy getting other things to work and I'm not ready to implement the manual cleverness just yet. What I could do is put an assertion in there, but that will hide traps in the code that I will likely forget about and will come back to surprise us who knows when in the future. So there won't be a warning when I translate code that uses foo. Making it a static assertion won't work because that won't compile even before foo is being used anywhere. There's a D feature that fits the bill perfectly, although it's not intended for this purpose. If I mark the code as deprecated, it will still compile everything and without notifications. But as soon as code that uses foo is compiled, the compiler notifies me with a deprecation message. The term deprecation is a bit misleading, but it does raise a red flag, which is what I want, and prevent surprises down the road. Pascal uses the same keywords for logical operators and bitwise operators, and, or, and not. Now, Pascal 2D does not analyze enough of the context to pick the right operator, so it makes a guess. The good thing is that it can inject static assertions that force the decompiler to verify the correctness of the guess. A static assertion is performed at compile time, so you are quickly given an opportunity to fix the translation before it is used at all. And essential is that these assertions are temporary assertions. When everything compiles and without errors, a switch in the transcompiler is flipped, and I can transcompile again, and the correct code is generated cleanly. In this recommendation, the recommendation is to use a different keyword that does the exact same job as logical AND, namely and then. I think I'll just skip through some more of them quite quickly. You can watch back the video and at half speed. This is showing the bitwise negation. Delegates. It does the wrong thing here because it misses an ampersand in the call on the D side. So I do that with an extra comment. If it's not a nested function, but a module level function, then toDelegate comes to rescue from std functional. And what I don't have time to go into, the most difficult case is strings. To support the Pascal strings in D. There are issues with file I/O. We are preserving binary file compatibility with our old files. And also string indexing. In Pascal, they start at 1. In D, they start at 0. Capacity in Pascal is a compile time constant, mostly, unless you allocate them dynamically. In D, they're not. So I think we'll take the rest of the time for any questions. This is the takeaway. Thank you.
All right, so like the man said, it's question time. Raise your hand if you have a question. Oh, 3 at once. 1, 2, 3.
Is there something very unique to Pascal that makes this possible? Or do you think that the same approach would work well for other languages?
This pragmatic approach depends on language similarities. So one of the similarities is nested functions, which will require a lot of modifications and rethinking if the target language would not support nested functions. So I think that's a requirement. But in principle, yeah, D is so powerful, especially with the introspection and the static assertions, that you can do whatever assumption and heuristics, you can verify them. And they won't be an artifact in the final translation. So I think that matches very nicely.
Did you run into any trouble with the order of the parse tree? Like if you have a function name and function arguments, they need to be in a certain order?
I had one problem with the associativity of an array declaration of arrays, I think it was, which required a reordering of the parse tree, and I could accomplish that with semantic actions. Ali.
How is the acceptance in the among the colleagues of D? Are they ready? Are they waiting for it excitedly, or how is it?
Yes, I think so. They are watching now online, so they won't be here to answer that. Maybe we can dial in. Yes, most of them, definitely. I think all of them. Of course, the most convenient thing would be to just continue as ever. But everybody is aware that this can't go on forever. So it's a necessity to find something else, and the choice fell on the in-committee. So I think there's a general trust on that the committee made the right decision.
All right, well, that's about all the time we have for questions. So
thank you very much.
Thank you.